Hello students, this is Professor Chalai, and in this lecture we're going to look at naming ionic compounds. Now, nomenclature is just a fancy word for the system of naming things, and as I mentioned in our last lecture, we need to name things in order to be able to study them in an efficient manner. And as always, you can follow along with our Chapter 2 workbook. But for ionic compounds, to name them, it's simply just the name of the cation and the name of the anion put together. Remember, cation has a positive charge, the anion has a negative charge, and that's it. If you know what the name of the cation is and the name of the anion, that's it. That's all you need to know for naming ionic compounds. If you scroll down in your workbooks, there's this entire long list of tables of cations and anions of different types, and if you memorize them, that's all you need. Really, that's all you need. You need to memorize the formulas and the charges, but that's all you need. And we can end the video right here. But there's some strategies that can help you remember the names of the cations and anions that I want to talk about. And the first is dealing with monatomic ions. Remember, monatomic ions means they only contain one type of element. So an example of that might be NaCl. The cation only contains one element, sodium, and the anion only contains one element, chlorine. So for naming these, really the cation name is just the name of the metal. In this case, sodium. So the name for this would just be sodium for the cation. And then for the anion part, you take the base name of the nonmetal. So chlorine, the base name will be chlor, right? CHLOR. And instead of the ending, you replace it with ide, IDE. So it'll be chlor-IDE. So the name of this this ionic compound will be sodium chloride. I bet you all knew that before. If you wanted to break apart this into its charges, sodium is in the first group of the periodic table, which means it forms a +1 charge, so it'll be sodium +1. Chlorine is in the halogen group, the second to last column in the periodic table, so it has a charge of -1, and so we write it like that. The charge is balanced. Another example would be for MgCl2. The cation only has one element, Mg. The anion only has one element, chlorine. So this would be Mg is magnesium. The anion, again, the base name, chloride. Mg has a charge of +2 because it's in the second group in the periodic table, and chlorine has a charge of -1, but there are two of them, so the total charges in both balance out. So that's the first type of ionic compounds that only have one element for the cation and one element for the anion. We're going to come back to polyatomic in a second, but remember that on the periodic table, all the way up here, we talked about how the first row has +1 charges, the second row has +2 charges, and so on. But oftentimes, a lot of these elements in the transition metal, they could have various charges, multiple charges. And that's why I didn't tell you what kind of charge they form. For those elements that could have multiple charges, you put the name of the metal, but you put the charge in parentheses. A good example might be, let's do FeCl2. We know that chlorine has a charge of -1 and there are two of them. So in this example, iron has a charge of +2, right? To balance out the two negative charge. Iron is one of those. It's a transition metal that could have different charges. So here, what we will do is we write the name of the metal, iron. We write the charge in Roman numerals in parentheses. So iron 2 chloride. That's how we deal with that. This table that I've shown you earlier gives you examples of lots of elements that have various variable charges, like iron, tin, copper, lead, cobalt, mercury. They could all have multiple charges. And these are what those compounds look like. Basically, the charge is just a thing in parentheses. Iron 2, iron 3, tin 2, tin 4, and so on. So that's with metals that could have multiple charges. So that's the third one. Let's look at polyatomic ions, because really for these, there are some strategies, but for the most part, you'll probably have to try to memorize a lot of them. And I will go over some of the strategies right now. So for polyatomic ions, the one that I want to look at specifically are oxygen ions. Remember I mentioned that oxygen ions are anions with oxygen in them. And so what you really have to memorize is the name of the most common form of that anion. And I'll show you what I mean by that. So the name of the most common form is just the name of the anion with an ending that has ATE ending. So for example, oxygen ion has oxygen, so CO3 2 minus. This is carbon with oxygen atoms in an ion. The name is just carbonate, right? The ending is 8. This is the most common form of oxygen ion with carbon in it, so we call it carbonate. Phosphate, PO4 3 minus, is the most common oxygen ion with phosphorus, so we call it phosphate, right? The ending is ATE. And that's how we go about naming them. Sulfur with oxygen, this is the most common form, so we call it sulfate. Chlorine with oxygen, we call it chlorate, because that's the most common form. And so if you just memorize these most common forms, you can go a long way in remembering what these are. And then these other rules just come in if they have one more oxygen, one less oxygen, or two less oxygen than the most common form. What do I mean by that? Well, let's look at one of these as an example. So this is chlorate, ClO3 minus. If you have one more oxygen, ClO4 minus, your name now, you add a PER in front of the name to get the new name. So one more oxygen, this becomes perchlorate. What if you had one less oxygen? Instead of 3, you had 2 now, ClO2 minus. If you have one less oxygen, you change the ending from 8 to ite, right? So this becomes chlorite, right? And if you had 2 less oxygen, so instead of 3 oxygens, you just have 1, your name, you add a hypo in front of it. So this becomes hypochlorite. Those are the naming rules for the oxygen ions. You have to memorize the ones that are most common, and then using those, you can figure out the rules for the ones that are not as common, but they have either one more, one less, or 2 less oxygens. So you can figure out from this that if you have something like SO3 2 minus, it's one less oxygen. This would be sulf. Instead of 8, we change it to ite, because that's the rule for one less oxygen. So this becomes sulfite. That's the sulfite ion. If the naming rules are complex and you prefer to memorize, it's in the table. But some people prefer to remember it by naming rules. Okay, so those are with polyatomic ions and specifically oxygen ions, and how do we go about naming them. Let's now look at water of hydration. Because I mentioned previously that the way ionic compounds form is you have a positively charged cation, a negatively charged anion, and they attract each other, right? However, in crystals, what happens is this negative charge could attract another positive charge over here, maybe over here, and this positive charge here can attract another negative charge over here, maybe over here. This positive and this positive attracts another negative over here. So what ends up happening is each ion are bonded to other ions in this complex, what we call lattice, crystalline lattice. Crystalline lattice. And we'll talk more about these a little in more detail later in the semester. But what you end up happening in, for example, NaCl, you have an Na ion next to a Cl ion next to an Na ion, and it forms this long crystal three-dimensional structure, if you can imagine it. So yeah, this would all be three-dimensional. So the structure shapes can vary, But in a salt crystal, for example, NaCl crystal, sodium chloride, it would look something like this. Now, sometimes you can have situations where we have, let's say, a water molecule with an O and H's, and these water molecules will have tiny negative and tiny positive charges, right, on them. They can insert themselves inside of this crystalline lattice. For example, if you have a positive charge here, the negative charge, the small negative charge from the oxygen can be attracted to that positive charge, right? And then you have your hydrogen and a small positive charge, like that. So you have water that can fit itself in between our salt or crystalline lattice. This is our negative charge. So the water molecule fits itself in between the negative and positive ions. And in that case, we have a situation where we have water of hydration. The salt has water embedded inside of it. Now, the way we go about naming those, and there's some examples that I'm going to show you in a second, is you name the cation and the anion as normal, but you add how much water of hydration it has. For example, let's find a clean space. Okay, here. Let's look at this molecule. It's copper sulfate, right? So it's copper sulfate or copper 2 sulfate. It has a charge of +2. Sulfate has a charge of 2 minus. In between, for every one ion of copper and 1 ion of sulfate, we can actually fit 5 water molecules in between. I'm going to draw it like that. So the way we write it is put copper sulfate, we put a nice little dot there, and we put 5 H2O to say that for every 1 copper and sulfate ions, you have 5 water molecules associated with it. And then the way we name that is we write the name of the salt as normal, so it's copper sulfate, I think. Then we name the number of water molecules. In this case, it's 5, so that name would be penta for 5. If you want to know what those the names for the different numbers are, here they are. It's hemi for half, mono, di, tri, tetra, penta, and so on. This you need to memorize. There we go. Okay, so it's copper sulfate, the name of the ion, the amount of water, penta, and then hydrate, pentahydrate. Note that you could also have half a water molecule. Really what that means is for every 1 pair of cation and anion, you have half a water molecule, which means basically for every 2 cations and 2 anions, you just have 1 water molecule in between them. That's all that means. So that's the name of, that's how you name salts with water of hydration. You just use the prefix for the number, and then you use the word hydrate. And then finally, the last thing that I want to mention is if there's an H plus in front of the anion, this is how you name it. You add the letters, the phrase, I guess, by in front of the name of the cation and the anion. So, for example, if you had, we know that Na2SO4, this is sodium sulfate, right? And sodium has a charge of +1, and there's 2 of them. But if we replaced one of the sodium ion by like an H plus ion, we can do that. The formula becomes HNaSO4, right? The formula for SO4 is still SO4 2 minus. Sodium is Na plus, and the hydrogen is H plus. So the charge is balanced, 1 plus, 2 plus, and SO4 2 minus. And 2 minuses, so the 2 plus, 2 minus, they cancel each other out. But how do we name this? All we do is we add bi in front of the name. So this was sodium sulfate. This would just be sodium bisulfate. We add the bi in front of the anion, which means this here should actually be in front of the anion, not in front of the cation. Sorry about that. So you add bi in front of the anion. There we go. And that's how you name it. Sodium bisulfate in this example. So long drink of water to naming ions. And really what you need to know is all of these ions. If you can find a way to remember all of these ions, either by memorizing them or using the various rules to figure them out, then you're good. For this table, this column, for example, you probably have to memorize all of these because it's not as easy to figure out. In here, you could use some of those rules for how you name oxygen ions, like is it a sulfate, is it a sulfite, for example. The ones with the various variable charges, they're easy. The charge is the same as the number in parentheses, but you need to know which ones would have variable charges and which ones would not have variable charges. If they're in the first two rows of the periodic table, two columns, they won't have variable charges. So yeah, memorize all of these and try practicing number 14, 15, and 16 on your own in naming them or writing different formula. And you can pause the video and try them all. And when you unpause, I'll go over some of these. Okay, let's go over a few of them. PbCl4. Cl, we know it's a halogen, so it should have a charge of -1, and there's 4 of them. There's one Pb. Pb is lead, which means that to balance out the charge, it should have 4+ charge, right? Pb 4+. Do we see how we get that? 4Cl minus, which means the plus charges should be 4. So if Pb has a charge of 4+, it should be lead 4 chloride, right? Chloride. That's how we name that one, lead 4 chloride. This one is lithium dichromate, right? Lithium is the ion. It's 2 lithium with a +1 charge because lithium is in the first group. And Cr2O7 is one that you really needed to memorize. Cr2O7 2-. That's the charge there. And that's a dichromate ion. Okay. I won't go over the naming for this one, but it's in the table. It's ammonium hydroxide. This one, sodium, right? That's the name of the ion, but there's an H inside, so it's bi. This ion is carbonate. Carbonate. People write the H either in between or in front. I don't know if there's a standard rule for that. Okay, this one has water of hydration. So the ion is copper sulfate. So copper, what's the charge? Sulfate has a 2- charge, so copper must be a 2+ charge. Copper 2 sulfate. And now for the hydration, penta for 5 hydrate. This one, let's use a different color. Calcium sulfate. Calcium can only have a +2 charge because it's in the second group. Calcium sulfate, half of a water, so half is hemihydrate. There we go. We talked about what a half a hydrate means earlier. Now let's do the opposite. Let's write the formula for the following ionic compounds. So tin has a formula of Sn. 2 means it has a 2+ charge. Chlorate, the ion chlorate is ClO3-. If you remember from our chart, was one we had to memorize. So this formula is simply Sn. Now we have to balance charges. This has +2 charge, which means we need 2- charges. So to make 2- charge, we need to multiply the whole thing by 2, right? So we'll need 2 chlorate. So the way we do that is we put the chlorate, ClO3, and we put a little 2 outside the parentheses to show that everything inside of the parentheses is multiplied by 2. So this is tin chlorate right here, right? Tin 2 chlorate, and all the charges nicely balanced. Let's try this again. cobalt 2, right? Cobalt 2 means 2 plus charge. Phosphate, let's use a different color. Phosphate, if we memorized for phosphate, it's PO4 3 minus. All right, here's a tricky one now. We got 2 plus charge and 3 minus charge. How do we balance them out? Well, in these tricky cases, we just take the number of plus charges, we multiply that here. We take the number of minus charges, it's 3, and we multiply that here. So we got 3 times 2, that gives us 6 plus charges. And we got 2 times 3, that gives us 6 minus charges. So they're going to balance. So how do we write it? Well, let's see. Cobalt, we need 3 of them. It's only one element, so we can put the 3 right here. We don't need parentheses. PO4 3 minus. PO4 3 minus. We don't put the charges. And we need 2 of them. And there we go. Cobalt phosphate. Try one more. Barium chloride hexahydrate. Let's do this one at a time. Barium, Ba. If you look at your periodic table, it's in the second group, which means we already know it has a 2 plus charge. It's not variable. Chloride, we already know, has a charge of Cl minus. So already we're seeing for 2 plus charge and a 1 minus charge, we need to multiply that by 2 so that the charge is balanced. And then finally we have the hexahydrate part. Hexa means 6 H2O, right? So if we put this all together, we have Ba. For the chloride, we need 2 of them, so Cl2. And then for the hexahydrate part, we put a little dot there, 6H2O. If you have any questions naming these, just let me know. But this is a huge part of what you should know for this chapter, naming ionic compounds, and all of the things on this table I sort of expect you to know certainly by the end of the course. I'll see you in the next lecture when we go on to name molecular or covalent compounds. See you then. Bye.